Okay, so our last chapter we're going to look at, before we start trig, it's two kinds of functions, exponentials and logarithms. Okay, so we're going to start today with exponentials. Okay, so first, I just want to look at the difference between those two things. Okay, they both have an x and a 2 in them, but they're very different. In each case, we have a base and we have an exponent. Okay, when we look at that x to the second power, x squared, what's the base? Yeah.
The x.
The x. And what's the exponent?
2.
To 2. Yep. And the one next to it, 2 raised to the x. The base is a 2. And the exponent is the x. Okay, the big difference between something being a polynomial and then something being an exponential is that the variable is in the exponent. Okay, that's one of the things that you need to have to be an exponential function. Variable has to be in the exponent. And because the variable is in the exponent, that causes these kinds of functions to grow very rapidly or decay very rapidly. So there's two kinds we're going to look at, a growth and a decay function. Polynomials, like x squared, it still can grow quickly, but it will not grow as fast as an exponential. Exponentials get huge, okay, very, very quickly. So when we studied polynomials, this is the definition that, one of the characteristics we described. Okay. To be a polynomial, the variable is in the base, and the exponent had to be a non-negative integer. Okay. That's polynomials. That's what we did before. So now, when the variable is an exponent, so I told you that's one of the things you need to have. The other thing is the base can't be a 1. If the base is a 1, even if the variable is in the exponent, that would not be considered exponential. Why not? Why can't the base be a 1 and have it be exponential?
It won't change, it'll be linear.
Yeah, this is basically just like graphing y equals 1. That's a horizontal line.
So that's not even linear then.
Well, it depends on how you define it. It is a constant function, yes, which is a horizontal line. I think in our book, to be linear, it has to be like y equals mx plus b, which that is not. Okay, so that's a constant function. All right, so if the base is anything other than a 1 and positive, it's considered exponential. We don't look at what would happen when the base is negative. Okay, we get some kind of weird behavior, like if you tried to do this, let's say -2 to the x. That's not something you can even really graph. Okay? Because if you started to try to make a chart of values for that, let's say x is 1. What do you get if you raise -2 to the first power?
-2.
Okay, so that's -2. All right. How about if you plug in 2 and you raise -2 to the second power?
Positive.
You get +4. And then if you plug in 3,
-8.
you get -8. So first of all, you're getting a graph that's kind of like oscillating positives and negatives. And now, let's say you did something like this. Plug in a half. When you raise something to the 1/2 power, we talked about this in chapter 4.
It's like taking the square root.
It's like taking the square root. Well, what's the square root of -2?
1 point something I.
Yeah, it has I in it. So if you try to take the square root of -2, now all of a sudden you went from something that's oscillating positive and negative, now you have an imaginary value in it. So yeah, it's non-real. So you can't even really draw that kind of thing. So the base can never be a negative number. Things start getting really weird when that happens. But even though we can't do 1/2, you could do 1/3. because raising to the 1/3 power is like taking a cube root. That's an odd index. That's fine. You could take the odd root, the cube root of -2. So some fractions you can do, some fractions you can't do. Some are positive, some are negative. So we've got to focus when the base is a positive real number, but not 1. That's what makes it exponential. All right, let's graph an exponential and just take a look at it and see if we can look at the domain. Okay, I'm going to graph a pretty common exponential. I'm going to do 2 to the x. So 2 raised to the x. Okay, and all of a sudden, once it gets past the y-axis, you see it curve up very quickly. So if I graph 2 to the x, does anybody have a guess based on that graph, looking at how far left and how far right it goes, what the domain is going to be? Yep.
Infinite.
Yeah, the domain is from -infinity to infinity. All exponential functions have a domain of -infinity to infinity. You can plug in any number for the exponent, for the variable. Now, how about looking at the range? Does it look like, at least in that exponential function, does it look like the graph goes down forever and up forever? What do we think? Yeah?
It certainly goes up forever, but not down.
Right. It does go, exponential functions will always go in one direction when you're talking about range forever, but they won't go both. Okay? How could it go the other way? Well, you could reflect it. You could flip it. Okay? And then it could go down forever. But this particular one starts at 0 and it goes up to infinity. It also never reaches 0. Okay? If you look at the graph, it comes down and it gets very close to the axis, but it never reaches it. That's because if you take 2 and raise it to a really big negative number, let's try like -10, you'll notice the number starts getting smaller and smaller. But bless you, what does that really mean if you wrote it with a positive exponent? Yep.
Wouldn't that be like 0.0000?
No, that would be like 1 over 2 to the 10th.
Right. 1 divided by 2 to the 10th. 2 to the 10th, big number, right? You have a really big number in the bottom of a fraction, it's going to make the entire fraction smaller. But even if I make that number -700, it's still going to be 1 divided by a huge number. 1 divided by a huge number is never 0. It gets close, but it never reaches it. Okay? Any question on that idea? And this is just restating what I said earlier. The base has to be a, well, actually, you tell me. How do you read that? What does that say? Yep.
A is in the set of all positive real numbers, and
Yep.
A is not equal to 1.
Exactly. A has to be a positive real number, but it can't be the number 1. And that's what we wrote in words on the other page. Okay, so these are all examples of exponential functions. Okay, they all have a base that's a positive real number, not equal to 1. And they all have exponents for the variable. Okay. Remember, the base doesn't have to be rational. Pi to the x, that's definitely exponential. The base just has to be a number that's positive and not 1. Okay, so those are all examples of exponentials. How about looking at these? So under the non-exponential functions, what kind of function is f of x? Yeah,
Polynomial.
that's a polynomial. It's a variable base and an integer exponent. Okay, that's a polynomial. How about g of x under non-exponential? Somebody tell me what g of x is? Yeah.
Another polynomial?
That's another polynomial, yeah. If you could think of it this way too. It's just 1/2 x to the 4th. That's a polynomial. And then the y equals under non-exponential, that's not really, I don't really know how you classify that. It's a combination of a rational function, but it also has a radical in the top. So it's like a mixture of the two.
Oh, weird.
But it's definitely not exponential. So any questions on what makes the top group exponential and the bottom group not exponential? Yes?
It's a quantifiable base, so like 10 for I with an exponential exponent.
A variable.
I
exponent.
don't
Yeah.
think I would
That
classify as that.
Well, so pi is one set
Oh,
number.
I thought you said I, not pi.
Oh, pi, yeah.
Pi.
Yeah, no, I to the x would not count as exponential. Why not? Why wouldn't this be exponential?
It's not real.
It's not real. The base has to be a positive or real number. Yep. All right, let's look at the difference between 2 to the x and 3 to the x. They're both exponential. So I already have 2 to the x. Let's compare that to 3 to the x. And we're going to do zoom 6. Okay, so there's 2 to the x. And 3 to the x is going to be in red. And watch what happens when we do that one. How would you describe what's happening there if you compare 2 to the x to 3 to the x? Yeah?
At 0, they're equal, but
Yep, and they both cross the y-axis at exactly the same point.
at negatives was higher up than the red.
Yeah, they do switch places right when they cross the y-axis. To the left of the y-axis, the blue one is above. To the right of the y-axis, the blue one is below. Yep, exactly. And what happens after you cross the y-axis is because the red one is 3 to a power, that's going to curve up quicker than 2 to a power. That's basically what I was looking for there. Any questions on that? Generally, we don't compare graphs with different bases to each other, especially when we're doing transformations. Like if you're going to do a transformation of this, you would be comparing it to something that has a base of 2, like this. And hopefully, you would know the plus 1, that's a horizontal shift, and that would move it which way? Yep,
To the left.
to the left. Yep, we'll move it to the left. All right. We're not talking about transformations yet, but I'm just showing you an example of how you would compare two functions. They should have the same base if you're going to compare them. Okay. So this question was a little different. That's why we use the calculator. Okay, so one thing we want to do is when we are trying to look at exponential graphs, it's going to be confusing if they have negative exponents. Okay, so it's going to be simpler to think about if they don't. So anytime we have a negative exponent, we can fix it so it's positive. And we kind of did that, actually right here. 2 to the negative 10, we rewrote as 1 over 2 to the 10th. How about a to the negative 1? How would you rewrite a to the negative 1 using a positive exponent? Ryan?
1 over a.
1 over a, yep. So we're going to use that idea to help us figure out something right here. So let's see if we can rewrite a to the negative x without a negative exponent. And we're really just going to use properties of exponents from Algebra 1 to do this. When you have a to the negative x, what is the coefficient of x, even though it's not written? Yeah? Right, there's a negative 1 there. I'm going to write that in. It's like having a negative 1. Now, that's a product. A to the negative 1 times x. What rule from Algebra 1 creates a product in the exponent? What would you have had to have in the problem if your exponent has something times something in it? Think about the rule for when you multiply two numbers together and that becomes your new exponent. That would only happen if you originally had a, yeah?
Two similar bases added?
So if you have two bases that are the same, like 3 to the 4th times 3 to the 5th, you do add the exponents and get 3 to the 4 plus 5 power. But I'm looking for a rule kind of like this, but you wouldn't add the 4 and the 5, you would multiply the 4 and the 5. When does that happen? Yeah?
If the 3 to the 4th was multiplied by, or like put to the 5th power?
Right, 3 to the 4th to the 5th, right? 3 to the 4th to the 5th. That would be when you would multiply two things together. Right? So that would be 3 to the 20th. So the only way that you could end up with something times something in the exponent is if originally those two things you multiplied together were powers. A power raised to another power. So you could have a to the negative 1 to the x. And up above, we just talked about what a to the negative 1 is. A to the negative 1 is 1 over a. So anytime we see something with a negative exponent, that is how you can rewrite it. You basically can flip the base, and then the exponent becomes a positive. So what if I had 3 to the negative x? What would that turn into if I rewrote it with a positive exponent? How about somebody other than the 3 in the front? You guys are doing great. Bye. Yeah.
1 over 3 in parentheses to the x.
1 over 3 of the x. Yeah, exactly. And you'll see why that's important later, because here, when you look at this, you might say the base is 3. But it's not really 3. It's 1/3. And when the base is less than 1, that causes the graph to do something different than when the base is more than 1. Okay, so we're going to learn what happens when the base is bigger than 1 and what happens when it's smaller than 1. And it's just easier to see that if you write it without a negative exponent. Okay. In this particular case, this graph would be what we call decay, because the base is really less than 1. In a graph like this, that would be growth, because the base is more than 1. So any questions on how to rewrite something that has a negative exponent and turn it into something that's a positive exponent? Okay, so now let's graph these, but let's fix the bottom one so it doesn't have a negative exponent. Nick, can you fix that bottom one for me so it's has a power of x? Right. And the reason why, we just went through that formula right here. The base basically just gets flipped, and then the exponent turns positive. Okay, so now we're going to graph 2 to the x and 1/2 to the x. And once we graph both of them, what I want to focus on is the domain and the range of each of them. Okay, so you could type in 1 divided by 2 in parentheses, or if you want to avoid parentheses, just do 0.5 to the x. And do zoom 6. Okay, so 2 to the x we already saw. And now you're going to see 1/2 to the x. All right. If you had to describe those two as a transformation, anyone think they could tell me what kind of transformation you could do to the blue one to change it into the red one? Yes?
Reflected over the y-axis.
Yeah, they are reflections over the y-axis, and that will always happen. You know, if I did a 3 and a 1/3 for the bases, or a 5 and a 1/5. Yep. Whenever you put a negative number, or a negative, inside the exponent, okay, a negative inside the exponent is a horizontal reflection. The exponent is going to be all the horizontal transformation stuff. Anything that's outside the exponent is going to be your vertical transformation, okay, when we get to that. All right, so let's put that up there. And now, let's see if we can figure out the domain and range of f of x and g of x. Well, they're both exponential. And what did we say about the domain for any exponential function? Yeah. It's all real numbers. Okay, so really shouldn't even be any thought about domain. It's always all real numbers. So negative infinity to infinity, negative infinity to infinity. Okay, so now let's look at the range of f of x. F of x is the blue one. What does it look like the range is for the blue graph? Oh, Moises?
Including 0 to
Can you say it one more time?
parentheses 0 to infinity.
Yeah, parentheses 0 to infinity. It never reaches 0. Never reaches 0. And how about the range for g of x? G of x is the graph in red. Yep.
Wouldn't it also be parentheses 0 to infinity?
Yeah, it would be the same thing because they're just horizontal reflections of each other. The horizontal reflection is not going to change the range. Okay? Not in this case. Okay? It does nothing to the range. Now, we looked at that specifically with a graph that had a base of 2 and a 1/2. But we can generalize that to any value of a. Okay, so here we looked at when a was 2. Now here I'm going to generalize it to a being any number. 3, 4, 5. Doesn't matter. So if you want to color code it, just to kind of know, like the a to the x, that's the type of graph that looks like one in blue. And g of x is the type of graph that looks like the one in red. So let's start with the blue one. How would you complete what I have up above? For graphs that look like the blue one, as x approaches infinity, what does f of x approach? No, not for the blue type of graph.
Infinity.
It approaches infinity, yeah. As x approaches infinity, f of x also approaches infinity. James, how about as x approaches negative infinity? What happens to y in the type of graphs that are in blue? Yeah, it approaches 0. Yep. So this is just asking what happens as you head left and right on each of these kinds of graphs. Now, g of x, that's the type that would be a fraction. 1/2, 1/3, something like that. So Cole, as x approaches infinity in a graph that looks like the red one, what does g of x approach?
0.
Yeah, that approaches 0. Yep. And on a red graph, if as x approaches negative infinity, g of x approaches positive infinity. These are just switched because they're horizontal reflections. So any question on that? Just kind of generalizing what we did before. So the key difference between the type of graphs we had in blue and the red ones is whether the base is above what number or below what number. What number is going to make the difference here? Between something being what we call exponential growth and something like exponential decay. How about Cecilia? What number do you think makes the difference? Oh, yeah, sorry.
I'm not sure.
Anybody help her out? What number do you think is going to cause this graph to change from looking like the blue one to change to looking like the red one? Yeah.
1.
Right. It's going to all have to do with whether the base is above 1 or below 1. If the base is greater than 1, that's going to be what we call an exponential growth function. If the base is between 0 and 1, it's exponential decay. And what if the base is negative? Then it's not exponential, right? So that's what we want to remember for this part. And remember, if the base is exactly 1, that's also not exponential. That's just a constant function. Yeah.
What's the second word?
The key difference between, yeah. And down below, I was just proving that they are reflections of each other. We saw that graphically, so I'm not going to get into that right now. All right, so transformations. The transformations on exponentials work exactly the same as transformations we've done on every function all year. So again, I'm not going to write down the whole chart. I'll put something up there and we can kind of go through it verbally. If you want to write anything down about it, feel free. All right, so let's say we had some kind of base. Which I don't want to use A because that's one of the letters I use when I do transformations. I'll just pick a specific number, but understand this works for any number. So let's say 2 to the dx plus or minus A times C plus or minus D. And again, this is your base, which can be any number. Okay. What would the A do? It's adding or subtracting, and it's inside the exponent. Yeah?
Horizontal.
Yes. Anytime you're doing something inside the function, that's a horizontal transformation. And because it's adding or subtracting, it's a shift. Remember, it's backwards. Positive is going to shift left. Negative is going to shift right. How about B? What kind of transformation is that going to be? Yeah,
Horizontal stretch.
that is a horizontal stretch. The bigger you make B, the more squished it gets. So if B is 5, that would really be a horizontal stretch by 1/5. If B was 1/3, that's a small number. Small number makes it bigger. Okay, if B is 1/3, that's a horizontal stretch by 3. Okay, so anything inside here, that's your horizontal. How about times C? What kind of transformation do you think C would be? So it's multiplication like B, but it's in front. Yeah, that's a vertical stretch. And it is not backwards. The bigger you make c, the bigger it stretches. c is 5, vertical stretch by 5. c is a half, vertical stretch by a half. And how about d? It's like c because it's on, bless you, it's on the outside, but it's addition or subtraction. So what's d going to do? Yep, that's your vertical shift. Up is positive, down is negative. If b or c is negative, we already saw what happened. Those are reflections. If c is negative, it's a vertical reflection. If b is negative, it's a horizontal reflection. If it's not in this format, you need to fix it so it is. All right, so that's the format that we're looking for. Okay, that one looks fine. It's in the right format. We can work with that. Notice the base is the same, because when you're doing transformations, you've got to compare something with the same base. All right. So first thing, can anybody tell me how many transformations that it would take to turn f of x into g of x? Just how many? Yep.
There are 3 transformations.
There are 3. Yep. So let's list them. You do have to list them in a certain order. The order you follow is horizontal shift, horizontal stretch, horizontal reflection, vertical stretch, vertical reflection, vertical shift. Okay. So B can give you 2 transformations, a stretch and a reflection, and C can give you 2, a stretch and a reflection. So between those, you've got 4. A is 5, and D is 6. So you could have up to six things in the same problem. Okay. What's the first thing that needs to happen to change f of x into g of x? Yeah.
Shift left 1.
Shift left 1. Yep. Perfect. So shift left 1. Okay. What's the next thing we would have to do after we shift left 1? Yeah.
Stretch by a factor 2.
Can you be a little more specific?
Vertical stretch.
Vertical. Yep. Vertical stretch by factor of 2. And after we shift it and stretch it, what's the third thing we would have to do to make f of x into g of x? Yep.
Shift down 5.
Shift down 5. So there's really nothing new with transformations, as long as you understand that template that I wrote up. Okay. Does anybody have any questions on what the A, the B, the C, or the D do, and how they apply to this problem? Okay. So this one is asking us to show that these two things are exactly the same. And this is important because when you start solving answers, and I ask you to maybe come up with an equation that's exponential, there might be more than one way to write your answer. So if it was multiple choice, and let's say you came up with the top one, you'd have to understand that that is the same as the bottom one, if that's the choice I wrote. So the way that you do this is you pick one of them and you try to manipulate it and turn it into the other one. Doesn't really matter which one. I would probably start with f of x and see if we can do some operations to it to turn it into g of x. Okay. Anybody think they see the first thing we could do that would start to make f of x fit at least fit the pattern of how g of x looks? Yeah.
Switch the 2x with the 3x.
Yeah, so how would you rewrite your exponent?
negative 2x plus 3.
Okay. So if we're trying to prove that two things are equal, it's probably a good idea to at least get the exponent in the same order. Variable first, constant second. Okay. Now, the next step. What number do we have in front of x right now? Yep,
-2.
-2. What number is in front of x in this one?
There's nothing for it. One.
There's a 1. So we have a -2. We want to have a 1. How could you make x have a 1 in front of it in our problem instead of a -2? We can't divide because we're just manipulating an expression. So we can only divide if we had an equation and we were doing something on both sides. But we're just changing an expression. So we need something we can do to this to make the x have a 1 in front of it instead of a -2.
We can let the, like where it goes to a fraction, right? Where it goes 1 divided, or would it be like 2 divided by 2? Let's see, it's the x plus 3. Where is that?
I'm not sure. I don't think so. Yeah.
Raised to -1 now.
Okay, so we are going to end up with something with a negative exponent in a second, but there's something I want to do first, just focusing on this. How would you create a 1 in that spot? What could you do so that -2 wasn't directly in front of, right next to the x anymore, but maybe we had something else there, yeah? Factor, yes. Factor out that -2. Now that's going to leave you with something in parentheses that has a 1 in front of the x. What would that leave you with inside the parentheses? Yeah,
X minus 1.5.
x minus 1.5. Because if you distribute the -2 back out, you get -2x plus 3. And we got a minus 1.5, which is something else we were supposed to have. So just by trying to make the coefficient of the x match, we automatically get the other number to match. Okay, now what can we do with that? Yep.
Find 2 to the power of -2.
Yeah, what's another way of saying 2 to the -2? Say I don't want to have a negative exponent here. What's another way of writing that? Yeah?
1 over 2 to the second, or 1/4.
1 over 2 to the second. That's really 1 over 4. And what is 1/4?
0.25.
0.25.
Okay.
And that's exactly what they wanted us to turn it into. Okay, so not a lot of steps, but you do need to know how to factor and then rules of exponents and how to get rid of a negative exponent. And the bottom way, I would say, is a better way to write it. G of x is a clearer way of looking at it because this is a decay function. If you look at it at the top one, you might see the 2 and think that's a growth function. Well, it's a growth function, but there's a reflection in it. So it's a growth reflected, which is really decay. So it's just easier to think about it the bottom way if you want to be able to quickly look at it and say, is it growth or is it decay? That's a base less than 1. And the variable is an x without a negative. Okay, if you've got a negative in front of the x, that's going to change how you have to think about it because something's going to get flipped at some point. Okay, any question on that one? That one I'm not going to talk about right now. We're going to talk more about that when we get into logarithms. That'll be another day. All right, so the last thing we want to get into is looking at some formulas. Okay. So let's say that we have a population that's increasing exponentially. if a population is increasing exponentially, that means it's increasing at a percentage. Okay? Compare that to saying the population is going up by 100 people every year. That's not exponential. That's linear. If you just add 100 to something over and over, that's straight line growth. When you're going up at a percentage, like the population of the town is going up 2% every year, that's a curve. Okay, that's going to be exponential. So what I want to do is see if we can kind of come up with a generalization for what the population is at a certain year, and then eventually, what is the population after t years? And see if we can get a formula to predict the population any number of years after the start. When the time is 0, that's a population like at the beginning. Okay, there's no time has gone by yet. What is the population of the town when no time has gone by in this problem? It's like the beginning. P. So the population is P. All right, so now, let's say I want to increase the population by some rate. Okay, it'll be a percentage. For this problem, we're going to assume that people don't move out of the town, people aren't dying off. So when we go to year 1, let's say January 1st, right? Year 1. What's the population the very first day for year 1? Yep.
Wouldn't it be P?
It'd still be P, right? Because we haven't added to it yet. Okay, so the very first day of the year, the population is P. Throughout the year, the population is going to grow. Let's say that the population was, I don't know, like 100 people. And I wanted to grow that by 2%. How do you take 100 and grow it by 2%? What would be the operation you would do mathematically to take the number 100 and increase it by 2%? Yeah?
Would it be, what's it called? 100 times 1.02?
Yes. To find the amount of increase, right? You basically can take your population and you can multiply by 1.02. Now, that's good because that gives you the final answer. But let's say I just wanted you to figure out the number of new people. What would you multiply 100 by if it was going up 2%? And all I want you to do is figure out the amount of people that are going to be added to what you started with. Yeah?
Then you multiply by 0.02.
Yeah. And the 0.02, that's the way the problem is going to be worded when we get it. They're going to give you a growth rate as a percentage. If you take what you started with times your growth rate, that gives you the amount of new people in the town. So then your formula becomes the number of people you started with plus, we'll just say, so this is what you started with. This is the new people that are going to be added. And when you combine them together, that's the new population of the town. How could that be simplified? Or actually, we kind of did this on the last problem. What could I do to P plus P times R to write it a different way? Yeah?
2P times 1/2 R.
Well, these aren't like terms, so they can't be added together because one has an R and one doesn't. But there's one thing we could do to rewrite it. We did this earlier today. Yeah?
Oh, PR plus P.
PR, that's what we have right now. PR plus P. P plus PR, PR plus P, the same thing. But I'm looking for, it's not just using the commutative property, it uses another property. What do those both have in common?
P.
P. So what could we do then?
Factor.
Factor it, yeah. If you factored out the P, what would you be left with?
R.
What would be your whole expression?
P times R.
P times R is just this.
P plus P times R.
Yep.
P times 1 plus R.
P times 1 plus R. If you can't think of it that way, we're going to have a problem. It's not going to work. So we have to think of it as P times 1 plus R. Okay, that's your new population. Now, let's figure out the population of people at year 2. Okay? At year 2, we're starting with a certain amount of people, and we have an amount of new people. What's the population that we are starting year 2 with? So we'll do what we did to get from year 0 to year 1, and we're going to do the same thing to get from year 1 to year 2. We're going to have a start, and we're going to have a new. The start's the easy one. The new, we've got to think about that a little bit. Yep?
We start with P times 1 plus R.
We're starting with P times 1 plus R, because that's what we ended year 1 with, so that's what we start year 2 with. And now, what did we do with our starting population to figure out the amount of new people? Don't even, just, you can answer that very generally. What do you do with the start to figure out the new? Yeah?
You add P R.
Well, that was only for year 1. We added P times R, but in general, to get the new, take the start and do something to it. Yep?
Multiply it by R.
Yes. Take the start and multiply it by R. Okay, so once you know your start, multiply that by R. So my start was P times 1 plus R. My new is P times 1 plus R times R. And now let's simplify that. Actually, you know what? Might be easier to think about. Instead, if I put the R there, I'll put it at the end. It's the same thing, but it might make something a little more obvious. What do both of these have in common now?
R.
More than R.
P R.
Yep.
P times 1 plus R.
They both have P times 1 plus R. So now factor that out. P times 1 plus R. If you factor out P times 1 plus R from the first one, what's left? 1. And if you factor out P times 1 plus R from the second one, actually it looks better down here, what's left there? Just the R. And what's P times 1 plus R times 1 plus R? Yep.
P times 1 plus R to the second power.
P times 1 plus R to the second power. Yeah, I had some of this already written out. I was just kind of showing it to you as we went. So that's your population for year 2. Now to find your population for year 3, you would take what you're starting with, which is that, and you'd multiply by R to get the new, and you'd add them together. But does anyone think they see, I'll just put it right here, for year 3, what the new population would be without going through all that? Yeah? Lucas?
P times 1 plus R to the power of 3.
Yeah, P times 1 plus R to the power of 3. So now by factoring it, we start to see a pattern. P times 1 plus R to the first, P times 1 plus R to the second, P times 1 plus R to the third. So what do you think the formula would be for year T? Yeah?
P times times 1 plus r to the x.
Yeah, p times 1 plus r to the t. So by doing out the first 3 years, we start to see a pattern, and that's the pattern if we generalize it. That's the formula for exponential growth. That's an initial population. R is the rate of increase, but it has to be as a decimal. Right? So 2%, 0.02. 12%, 0.12. And T, I didn't label that one, but what do you think T stands for? Yeah, that's the time. So you'll generally be given 3 things, and your goal is to figure out, when you plug those 3 things in, what's the new amount? Could be people, could be bacteria, money, yeah, it could be all kinds of things. Yep.
Yeah.
So that's the exponential growth formula. Now, to do exponential decay, there's only one thing there that would change. Does anyone have a guess how that formula would change from growth to decay? Yeah?
Subtract r.
Right. It would be minus r. So if something's increasing at a certain percentage, you need the growth formula. If something's decreasing at a certain percentage, you use the decay formula. All the letters stand for the same thing. P is an initial amount. R is a growth rate, or in this case, it'd be a decay rate. And T is the amount of time that's gone by, usually measured in years. The T and the R would have to be measured in the same units. So if R is like, let's say your acres of forest is decreasing at 3% every year, then time would have to be measured in years. So it's important that the units match on the R and the T. Right. So if I said to you, the forest is decreasing at 3% every year, how much forest is left after 6 months? Well, you can't plug in a 6. You'd need a 0.5 for the T. Yep. Okay. So now let's try this one. So a town has a population of 50,000 people, increasing at a rate of 2.5% every year. So model that as a formula, and then use the formula to find when the population of the town hits 100,000 people. Okay, so we're going to do our population as a function of time. First of all, is this a growth or a decay problem? Yeah, it's growth because the population is increasing, and it's definitely exponential because it's a percentage. It doesn't say the population is getting 50 new people every year. That's linear. This is exponential. All right, what's the first thing that I need when I write an exponential growth formula? Yep.
The starting population.
Which in this case is how much?
50,000.
50,000. And what's going to go in parentheses next to the 50,000? Yep.
1 plus 0.025.
Yes. So you have to make sure you write your growth rate as a decimal. That's 0.025. So 50,000, we'll simplify that in a second. And what about my exponent? T. They didn't give me an amount of time. This question isn't asking after 20 years how many people are in the town. It's a little different.
It's 5.
So let's simplify that. 50,000 times 1.025 to the T. Okay, so there's your model. Now they want to know when the population hits 100,000. Where does that 100,000 get plugged in? T or P of T? Yeah? P of T. So now you're going to set that equal to 100,000. And the tricky part about solving that is you have a variable in the exponent. We haven't talked about how to solve with variables in the exponent. To do that, we need a logarithm. So how else can we solve that? Because we haven't talked about logarithms yet. something equals something. Yeah.
Divide by 50,000 on both sides.
Okay, yeah, you definitely could do that. You could divide by 50,000.
So that means you 2 equals, yeah. 2
Still have the problem of that variable in the exponent, but at least we do have a simpler equation now, so that's a good idea. So how else can I solve this now? Since I don't know logarithms, at least I haven't taught you them.
Can you use like root t both sides?
Well, then
You
you
need a
can-
logarithm to do that.
Oh.
So yeah, because we don't know what t is. Otherwise, yes, if that was a number, it would be a little different.
Kind of stuck down.
No, there's another approach we can use. How else can we solve that?
Graphically.
Graphically. So graphically. So plug in 2 in y1. Plug in 1.025. We have to use x in y2. And by doing it this way, we divided both sides by 50,000. That makes our numbers a lot smaller. We can get the answer in a standard window. Maybe. No, actually, not quite a standard window. It is starting to curve up, but it's a very slow growth rate. I mean, it's not even a growth rate of 1%. So it will curve up, but it's very slow. Let's set this to like 40.
It's a growth rate of 2.5%.
Yeah, 2.5%, sorry. And hopefully, I think 40 will be enough to see where they cross.
Yep.
Yep. So you can see it's starting to pick up a little bit the more time goes on. Second calc, and what do we need to find?
Intersect.
Intercept. So it's going to take 28.07 years. So the amount of time is about 28.07 years.
Huh. To like double your population. It's not that
To
bad.
double the population. Yep. So that's another way I could have worded this question. I could have said, tell me how many years for the population to double. Then you'd have to figure out, well, that means 100,000. Okay, but I gave you the 100,000 this time. Right. And if you happen to type in something like this, let's do log 2 divided by log 1.025, you get exactly the same answer. And that's what we're going to talk more about at some point.
Huh.
It's very easy to solve with a logarithm if you know how to type it.
Okay, so it's just taking one side of the equation and dividing by the other for logic.
Yeah, we'll talk more about
In a
it.
sense.
It sounds good.
So be careful when you are doing a word problem, whether you include negatives. Something like a population increasing, you can't have a negative amount of people, so you wouldn't want to look at the negative part of the axis for that. All right, let's look at this one. So this is going to be a very specific kind of exponential growth. This is something doubling. Okay, something doubling. So let's say we start with 100 bacteria, and it doubles every hour. See if we can look at a pattern and then generalize it. How much bacteria do you have at the start of the experiment?
100.
100. How many bacteria would you have after the first hour?
200.
200. Or think of it as 100 times 2. How much bacteria would you have at the end of the second hour?
400.
400. Or think of that as 100 times 2 squared. Now, how much bacteria would you have at the end of the third hour? But I'm more interested in you thinking of it this way. I know it's 800, but I'm more interested in that pattern because that's going to tell us the formula for T hours.
100 times 2.
100 times what?
100 times 2 to the third.
2 to the third, yeah. So it ends up being, well, see if you can tell me. What is this right here?
100.
It's 100, but what did it represent in our problem?
P.
P, that's like the initial amount. And what does this represent?
T.
T, which in our case is like the number of hours that have gone by. And the 2 is how you write down something doubling. So think about that the way we've written it before. It would have been like 100 times 1 plus my growth rate raised to my power. All we really did here was solve for what is the growth rate when something is doubling. What number would be in that box?
1.
1. So when something is doubling, a lot of people say, well, that means it's 200%. No, that's tripling. When something is doubling, that's a growth rate of 100%. That's why you get a 2. If that number was a 3, that would mean it was tripling. And that means this number right here would be a 2. So if something's increasing at 200%, that's tripling. 100% is doubling. So that's the formula in our problem, specifically for something doubling. In general, that's the formula for something doubling. It's an initial amount. There's a 2 here, because doubling is a growth rate of 100%. And this part, this is important. The reason that that number matched that number is because the bacteria was doubling every 1 hour. Let's say the bacteria doubled every 3 hours. After 9 hours, how many times would something have doubled if it doubles every 3? Yep.
3 hours.
It would have doubled it 3 times. 3 times. Right? How about after 12 hours? If it doubles every 3, how many times would it have doubled?
4.
4. So this exponent has to represent essentially the number of doubling periods that have happened. If something doubles every 1 unit, then your time will match the number of doubling cycles. If it's not, then you need to do this calculation. Okay? So if something, say, doubles every 24 hours, you can't say that in 24 hours it doubles 24 times, because it's only doubling once every 24 hours. So this is the number of, I guess you could say like the number of times it has doubled. That's what the exponent represents. It's the number of times it has doubled. So to calculate that, take how much time has gone by and divide by the length of time it is to double. Let's look at this one. Suppose 100 bacteria are in a petri dish. When will there be 350,000? Okay, I just want to set it up because I think you'll, once we set it up, solving it is exactly the same as the population problem with the town. So what would be my formula for the amount of bacteria as a function of time? Okay, what do we start with? Look up there. Yeah?
Initial is 100.
Initial amount, so you start with that. Okay. What's going to come right after the initial amount? Yep. 2, because this problem is about something doubling. Doubling is a growth rate of 100%. So the quick way to just remember, it's a 2 when you're doubling. Times 2. And what would my exponent be?
It would be t
T divided by?
divided by 2, 1.
1, because the length of the time to double is every hour. So it would be t divided by 1. And I put divided by 1 just in case it wasn't divided by 1. You have to remember to divide it by the length of the doubling cycle, length of the time to double. And now they want to know when that hits 350,000. So would you plug that in for t or b of t? Yep. B of t, yep. You'd plug in 350,000 right here. And you could divide each side by 100 if you want to make the numbers smaller, but you're still going to have to graph it and calculate an intersect until we talk about logarithms. Okay, so that's doubling. The last form you're going to look at is the opposite of doubling. What would that be? Yeah?
I know it's halving.
Halving, yeah.
Oh,
So it's half-life. Yep.
halfway.
So the idea for a half-life is it's the amount of time it takes for half of that substance to decay. Usually that's talked about with like nuclear material because some nuclear materials have a very long half-life, which means once you create them, you can't get rid of them and they're going to be around for thousands of years. And it's going to take a long time for that substance to decay into something that's safe. So like if a substance has a half-life of 5,000 years, that means once you create this nuclear waste, 5,000 years from now, if you had 10 pounds of waste, you'll have half that. You'll have 5 pounds left. Right? And if the amount of levels that it has to be, like let's say it has to be under a pound to be safe, it's going to take a lot of years. After 5,000 years, you got however much, you're going to go another 5,000 years for it to cut in half again, and then like another 5,000 to cut in half again. So when we did doubling, our base was a 2. What do you think we're going to do when we're halving? Yeah? 1/2, because our growth, our decay rate is 50%. So think about the formula. It was 1 minus r. 1 minus 0.5 gives you 0.5. Okay, I think that's all right. That'll be our last one. All right, so let's we'll set this one up, but then it's also going to be very similar to the bacteria problem and the population of the town problem. So we have 20 grams or 5 grams of a substance, and we have a half-life of 20 days. So every 20 days, half of the material we have is gone. Okay, breaks down.
Very fast half.
So what would that be as a, let's say, the amount of our substance as a function of time? What's our initial amount? Yeah,
Our initial will be 5 grams.
5 grams. And this is a half-life problem. So what's going to go in parentheses to take into account that it's a half-life? Yeah,
Will be half.
1/2. And what's going to be our exponent in this problem? Yep.
T divided by 20.
Right, because that has to represent the number of half-life cycles. So if 20 days have gone by, 20 divided by 20, that is 1 half-life cycle. Okay, so there's our formula. And they want to know when there would be less than 1 gram remaining. Where would the 1 get plugged in? T or A of T? Is it a time or is it an amount? Yeah,
A of t.
it's an amount. Yep. So one way to do this is they want to know when there's less than 1 gram. Well, if you find out when there's exactly 1 gram, any time after that, it's going to decay more and there'll be less. So basically figure out where they cross and then tell me that the answer is anything after that number. Anything before that number and it's still going to be above 1 gram. We can practice another intersect tomorrow. Okay, so that's the homework. It kind of just did a lot of single questions. It just jumps around. Okay, but there's some problems in there on exponential growth, decay, the transformations, and just some graphs. So you will need a calculator for some of them. And we'll take a look at that tomorrow.